Welcome to the Explainer. So, if you're tuning in today, you've probably already nailed the qualitative basics of organic chemistry. You know the standard levers of nucleophilicity, right? Charge, electronegativity, solvent, steric effects, resonance, the whole shebang. But today, we're going for the graduate level upgrade. Our absolute main goal in this explainer is to transition you from that freshman chemistry intuition to real, research-grade quantitative prediction. We're moving from simply ranking nucleophiles by gut feeling to ranking them with cold, hard numbers.
To really set the stakes for this deep dive, consider this quote: "Qualitative rules are ordinal. Research-grade prediction requires cardinal data." Think of qualitative chemistry kind of like a basic tier list. This molecule is better than that one. But research-grade prediction, it's more like opening the advanced stats menu in a complex video game. You don't just need to know who the strongest character is, you need the exact mathematical magnitudes to accurately predict how the entire system's going to behave.
Here's our roadmap for today. First, moving beyond qualitative rules. Second, measuring reactivity with Mayr's scale. Third, orbitals and transition state energetics. Fourth, modern computational and isotope probes. And finally, biology and predictive synthesis. Let's get right into it.
All right, Section 1, Beyond Qualitative Chemistry Rules, Predicting Order.
The main issue with those rules you learned early on is that they only predict order. For example, a qualitative rule tells us that an iodine anion is a better nucleophile than a fluorine anion in water, or that a hydroxide ion beats acetate. That's just ordinal rank order. But honestly, these rules routinely fail when you try to extrapolate across different nucleophile classes, like say comparing an anionic nucleophile to a neutral one. And that is exactly why we need the new paradigm, cardinal rate constants.
And this brilliantly illustrates the shift we're talking about. We are totally replacing the old way of just drawing simple greater than signs with true quantitative prediction using precise k-values. By calculating exact rate constants, true prediction lets us compare completely different nucleophiles, electrophiles, and solvents, all on one unified numerical scale. It's a real game changer.
Moving on to Section 2, Measuring Reactivity, Mayr's Scale.
This brings us to the first major tool for our upgrade, Herbert Mayer's Nucleophilicity Scale. When we break down this incredibly powerful linear free energy equation, it works like this. Log K equals Sn multiplied by the sum of n plus E. The n is the intrinsic nucleophilicity parameter, E is the independently tabulated electrophilicity of the partner, and Sn is the sensitivity. For context, enamines have a high n value of around 13 to 18, while halide anions might actually be negative. What does this mean? It proves that nucleophilicity isn't just some fixed inherent property of an atom. It's a measurable, fluid relationship against reference electrophiles.
Section 3, Orbitals and Transition State Energetics.
Okay, let's shift gears from the empirical data of Mayr's scale to the actual first principles physics of molecular orbitals. The mechanical why behind those old hard, soft, acid-base rules you used to rely on. That is captured in frontier molecular orbital theory, and it's formalized by the Klopman-Solom equation. This equation splits the total interaction energy into two distinct parts, electrostatic and orbital overlap. Hard-hard pairings are totally dominated by the electrostatic term, think widely separated orbitals. But for soft-soft pairings like large polarizable atoms, it's all about the orbital overlap term driving the reaction.
And that builds perfectly into Marcus theory. Now pay special attention to the intrinsic barrier here, denoted as delta G double dagger 0. That intrinsic barrier isn't just some abstract math. It literally represents the actual physical distortion required before bonding can even occur. It's a measure of how much the nucleophile and electrophile must stretch, deform, and reorganize their surrounding solvent shells completely independent of the overall thermodynamic driving force.
We can even apply these advanced energetics to ambident nucleophiles, like enolates. Instead of using vague heuristics to guess whether an attack happens at the oxygen or the carbon, we can use the curve crossing model. It quantitatively tracks the exact energy pathways. Early transition states are under charge control, which favors an attack at the site with the greatest negative charge. But as the reaction proceeds, the lower energy pathway switches to orbital control, favoring the site with the larger HOMO coefficient. It's highly precise, predictive regiochemistry in action.
All right, Section 4, Modern Computational and Isotope Probes.
So how do researchers actually observe these transition states in the real world? Well, they use kinetic isotope effects, or KIEs. By replacing a normal atom with a heavier isotope, like swapping hydrogen for deuterium, the reaction rate actually changes. A primary KIE, where the bond to the isotope is actively broken, can give a massive rate difference. We're talking between 2 and 7 for E2 eliminations. Meanwhile, an alpha secondary KIE helps researchers confidently distinguish between a concerted SN2 backside attack and an SN1 carbocation formation, just based on rehybridization.
Okay, let's dive into this. When applying quantitative solvent scales, that old polar A product versus product dichotomy is way too simple. Modern chemistry uses multi-parameter solvent scales so you can proactively predict solvent effects rather than just rationalizing them after your experiment behaves unexpectedly. The Comlet-Taft scale isolates hydrogen bond donating from bulk polarity. Gutmann's donor number quantifies Lewis basicity. These are the tools and let you mathematically predict exactly how a solvent change will shift your reaction.
Now, computational tools like density functional theory have completely mapped out the potential energy surface. In the modern computational view of the SN2 transition state, it's actually not always a single concerted barrier. Often, gas phase reactions of small anions proceed through a pre-reaction ion-dipole complex, and thanks to charge analysis, we know that bond breaking actually leads bond making. Basically, that means the SN2 transition state is often somewhat SN1-like in its charge character. Wild, right?
Final section, number 5, Biology and Predictive Synthesis.
Let's zoom out for a second and see how these exact same mathematical principles govern real-world systems. We can anchor all this complex math straight back to reality by looking at your own body. Enzymes exploit these exact nucleophilic principles every single day. Serine proteases use a charge relay system to generate a strong alkoxide-like oxygen nucleophile just to digest your food. DNA alkyl transferases use a highly reactive cysteine thiolate to attack alkylated guanine and restore damaged DNA. It is the exact same fundamental chemistry, just operating inside precisely organized active sites.
To sum up this whole upgrade arc we've journeyed through today, we can now directly compare the qualitative concepts you used to rely on with the powerful quantitative frameworks you've just mastered. We went from more charge equals more nucleophilic all the way to Mayr N values and FMO HOMO energy. We upgraded the incredibly vague soft prefers soft rule to the true mechanistic origin provided by Klotman-Salem electrostatic and orbital terms.
To make sure you can actually apply this, here is your actionable master checklist. This distills all that dense theory into a clear, step-by-step procedure for quantitative mechanistic analysis. 1. Determine if your problem is ordinal or cardinal. 2. Use Mayr values to compare dissimilar classes. 3. Decompose your barrier with Marcus theory. 4. Check if the transition state is early or late for ambident nucleophiles. 5. Choose the right quantitative solvent descriptors. And finally, 6. Verify your hypothesis against KIEs and computational data. So I want to leave you with one final research-level reflection question to really test your newfound knowledge. Explain, using the Marcus equation, how a reaction can be highly exothermic, yet still proceed slowly at room temperature. Think back to what we discussed about physical distortion and intrinsic barriers. Thank you so much for joining me for this explainer. Keep asking questions, and I'll catch you next time.